Next, we have Natalie.
Hi, my name is Astrid, and I'm a final year PhD student at the University of São Paulo, Brazil. And today I'm here to talk to you what to do before dealing with real data. So how to press graph neural networks to do truth-level simulation-based inference with galaxies. So this work was done by me and all the amazing people described here. And what and how we are doing this? We have a bunch of galaxies, and then we have all that information. We're translating this into graphs. We are feeding the graph neural networks, and we're inferring values for a megamatter. And we are doing this because graphs are a natural representation of the cosmic web. We're tracing all the structures of the galaxies, as you can see in this pictorial version. And graph neural networks are really good to deal with irregular data, as this is the case of these galaxies. And doing so, we do not have to impose any custom scale. But before talking about what are graph neural networks, I have to tell you what are graphs. And graphs can be seen by this other pictorial version here, where we have the nodes with the node attributes. So we describe graphs by this number, the node attributes. And then we have the edges, which are the connections between the nodes. And then we have the edge attributes. And the whole graph can have a global property, which is described by G here. So a graph is described by these three numbers. And then we use graphs to feed graph neural networks to get some answers. So behind this black box, we have an architecture. And in this work, we can say that this architecture is responsible to update the values of the nodes and the edge attributes. And after many blocks or many layers, we have a final representation of the graph that we have in question. So more specifically, the architecture that we're using is the message passing scheme, where we have an edge model, a node model, and then we are updating these values according to the nodes values and to the edge values in question. We have a multi-layer perceptron applied to these values. And then for the node model, we have the same case. So we have a multi-layer perceptron applied for the values of the nodes, for the values of the edges, and then we have the global property taken into account. And more than that, we have this symbol here, which represents the multipooling operation. And then we are taking into account an operation for the neighboring edges. And then we have the maximum value, the sum, and the average values. And this thing is applied in many layers or many blocks. At the end of the day, we have a last layer where we have all the nodes, and then we have this multipooling operation for the values of all the nodes and for the global property. And one more time, we have this simple multi-layer perceptron taking into account this array. So we have a galaxy catalog, and then we have the updated version taking into account the small and the larger scales. And then at the end of the day, we are inferring omega matter, which is an answer. And then we are inferring the mean and the standard deviation for omega matter. So this is not a simple architecture. So we are taking into account graph neural network together with a moment neural network. And then this is responsible to predict the first moment and the second moment. So we are doing so to obtain the mean and the standard deviation of omega matter. So our data set is composed by the CAMELS simulations, and this is amazing. And to have many variations of this, we have boxes with only 25 megaparsecs per each. And then we have variations in the cosmological parameters and in the astrophysical parameters. And we have different sets. The set that I will talk to you today is the L8 set, which follows for Latin hypercube, where we have variations for all the 6 parameters and different random seeds for each of these boxes. And then we have different models. So we have different subgrid physics models. So we have Astrid, IllustrisTNG, Magneticum, SIMBA, and then we have these two, which I can highlight as like SP28 is nothing more, nothing less than IllustrisTNG, varying more than only these 6 parameters. So we are varying 28 parameters. And then we have this other simulation, which is Swift Eagle, where it uses a Velociraptor to find the halo and sub-halo structures, different from these other simulations where we use subfind. And then I have to tell you that this was the first time that we have a robust model And what I mean by robust model, so every time that you train a machine learning model, you have to choose a data set. And you have a good model when you obtain good predictions. Most of times when you change the data set, the difference between these data sets ends up into something which absolutely does not work. So the model is not able to do predictions because of this difference in the data sets. However, when you have a robust model, this works no matter the data sets that we're taking into account. And then here we are using only the galaxy positions and the z component of the velocity. If you want more information, please take a look at the paper. And then we have a model which was trained on Astrid and tested on Astrid, SIMBA, IllustrisTNG, SB28, and Magneticum. And as you can see here by the plot where we have truth minus inference and the values of omega matter, this is working and all the metrics are pretty good. And this was the first time that we achieved something which does not depend on the subgrid physics models. But we would like to take into account galaxies, real observations. And then in this follow-up project, what we're doing is like we are incorporating observational effects into the data set and taking a look if if our GNN can deal with this real effects. So yeah, indeed, our machinery is working with masking effects, with uncertainties in the peculiar velocities, relative and additive. More than that, it is working taking into account uncertainties in the radial distance. And I have done this only taking into account the positions of the galaxies in 2 dimensions, and then the VZ, the velocity component in the Z component of the velocity. And it can take into account galaxy selections, for instance, color selection or star formation rate. And then this is just a summary of, just to say that this is working considering masking, velocity perturbations, and then blue and red galaxies. And it's important to say that this is not perfect yet, but all the predictions are working for at least 90% of the capsules. So these are the takeaway messages, and please reach me out if you have any questions or if you wanted to discuss something more. So you can find me just looking for Nathalie Desante. Thanks.